Hello students, welcome to a new course in this particular semester, namely the mathematical methods in physics. And in particular, we are going to discuss the vector spaces and function spaces. In particular, in function spaces, we will be dealing with the Hilbert spaces. So these are the two topics that are directly related to quantum mechanics in physics. So in the case of the mathematical methods, our discussion will be directly related to the requirements for the corresponding study of physics. That means it may be the electrodynamics or the quantum mechanics or the statistical methods. So what is the mathematical requirement for the theoretical development of the physics? Those topics we are going to study under the mathematical methods. So in the last semester, of course, we might have studied the foundation for the differential equations, both ordinary and partial, followed by some of the integral transform techniques for the solution methodology. So that was your discussion in the last semester, mathematical methods. And in this semester, we are going to deal with more generalization of the mathematical concepts. And the main topics in the second mathematical methods in the current semester are the vector spaces, function spaces. So that is that goes under one heading, and then followed by some kind of introduction to the tensors, and then the group theory. So overall, if you see, all the topics will be some kind of generalization of what is known to you under the undergraduate or from the school. So that is the overall idea. The concept is that when you are planning to go from the simple situation to the general situation, we use the word abstraction. So abstract means making the situation valid for several things. That means rather than saying that a particular rule is applicable only for a particular set of numbers, we say that we are going to apply the rule for a variety of mathematical objects instead of particular numbers. So moving from a particular situation to a general situation is what is known as abstraction, the concept of abstraction. So abstract doesn't mean something that is difficult to visualize. Abstract doesn't mean something too difficult to understand. That is not the meaning. So abstract means generalization. So how do we understand the mathematical world in a more general way rather than sticking to a particular topic? In particular, we can consider two-dimensional and three-dimensional Euclidean geometry that you already studied right from school, and where you learned the vectors, two-dimensional vectors, three-dimensional vector, the so-called IJK, unit vectors, etc. you learned. That itself is a vector space. The only thing is the terminology was not introduced at that time. So now we are going to say that the set of vectors that you already know in the Euclidean space, namely both in two-dimensional and three-dimensional, they themselves form a vector space. So if it is the case, so you need to understand what is this terminology vector space, and what is the generalization, or how are you going to move from the two-dimensional, three-dimensional, and from there where you are going to move. So that is what we are going to learn in this the first unit of this mathematical methods. So to start with, I would like to give an example with an equilateral triangle. So that's what is there on the background of this particular screen. So with this, I am going to introduce how we are going to generalize a particular situation to a general situation. How we are going to move. So what has enabled, or what is the idea behind generalizing a particular situation to a general situation? The concept is simple once you understand some of the things, and the easiest thing to start with would be to start with an equilateral triangle. So let us go to the board, and I would like to explain what is there in that. Okay. So let us start with this. Consider an equilateral triangle here, and which means that all the three sides of the triangle is identically the same, which is of course the length is not important for you. I have drawn it on a graph paper, and then I have shown the centroid of the triangle. So centroid is very important, and about the centroid I am going to rotate it. So let us rotate the triangle in the anti-clockwise direction, And as you can see that when it is rotated, we can always measure the angle. And now it is something like 30 degree. And let us rotate it completely. Completely. So now it is rotated by something like 180 degree, and then let us still rotate until it matches to the original. I am slowly rotating so that you see when the red color triangle will match with the black color triangle. So now it is matching. Now it is matching. So now if you see the angle, the angle is 120 degree. So if you now continue this rotation, I am going to make second rotation again. So let us rotate until the red color triangle has to overlap with the black color triangle. So I am going to measure it. So once this is overlapping, now it is overlapping. Now the angle is 240 degree. So earlier it was 120, now it is 240. We can still rotate. Okay, still we can continue this rotation once again and see when once again it will overlap with the black color triangle. So now it is already crossed 300, 320, 350, 360. So 360 degree, once again it is matching to the original triangle. So I am just coming to the counterclockwise to show that 3 times we have rotated. Okay, that means 3 sides. Each side when it is matching, we are getting 120 degree. So that is the starting point about our introduction. So what you saw from there is that what is that we want to understand from this particular example is that triangle is an element, or we say that it's an object. Okay, triangle is a mathematical object, and then we have taken, in particular, we have taken equilateral triangle. By that, what is an advantage is 3 sides are equal. This is the first point, and the second point is that the 3 of the angles are also equal, 60 degree. Whatever be the number, it's equal value. Now, because of the equal values of the sides and the angle, what happens is that more and more symmetry is present in the system. You have large symmetry, or we say high symmetry. If you are going to have non-equilateral triangle, then these kind of symmetries will be absent. You can't generate identical triangle by rotation by 120 degree. Not possible, isn't it? So that you can easily verify if you take another triangle where all the 3 sides are not at all equal. So that is the reason why we started with an equilateral triangle that has a property of equal sides and equal angles. And therefore what happens is this object is said to be a highly symmetric mathematical object. So highly symmetric, that is a point that we are going to catch now. What do you mean by that? Highly symmetric means it should have more number of symmetry elements. If you are going to have more number of symmetry elements, we say that the particular object is having high degree of symmetry. How many number of symmetry elements are there that we have to count? That is what we have actually counted. So we have taken a black color triangle and then we started to rotate that. That means a copy of that. What you mean to say is we take a copy of the black color triangle and rotate it. When you are rotating, I have shown it as a red color so that you can see the rotation with the black color triangle in the background so that you can see both of them. But if you are going to do an experiment, the original triangle only will be rotating. So that is a point that you have to remember. The most important thing is that the rotation has to be performed. So you see that where is the rotation taking place? The rotation has to be taken with respect to the centroid. So this is the centroid and the axis will be perpendicular to the plane. The triangle is actually a 2-dimensional object, right? Triangle is 2-dimensional object. And therefore, when the triangle is in the plane, the axis will be perpendicular to the plane. So like that you are going to rotate. Whether you are rotating clockwise or anti-clockwise, that's not important. So we are going to fix this point and then rotate. We are going to get back the original triangle. How many number of times? We got it 3 times, right? First rotation 120 degree. We got the triangle was appearing as if it was original. Remember, that is a point. After the 120 degree, the triangle appears to be as if it was the original configuration. It looks as if nothing was moved. This is the concept that you'll have to grasp. It means that it is equivalent to saying, how do you understand this is that if you are going to start with the original triangle, okay, take the original triangle, then you close your eyes. Once you close your eye, remember the configuration and close your eyes. Your friend will rotate the triangle by 120 degree and then stop it. Afterwards, you will have to open your eyes. After opening your eyes, you have to tell whether your friend has rotated the triangle or he did not rotate. That is what you have to tell. So if you perform this experiment, what is your answer? Your answer is you will be unable to tell whether your friend has rotated by 120 degree or not. That is what I mean to say. That means after the 120 degree rotation, the configuration of the triangle is identically the same as, or it appears to be identical as it was original. And we say that this is one symmetry element. One symmetry element, because we have performed one rotation of 120 degree. But if you perform any other angle like 60 degree, 90 degree, 45 degree, whatever be the angle that you perform, you can easily identify that the triangle was rotated. That means the configuration is distinguishable and therefore they are not symmetry elements. So this is clear. Okay. So once 120 degree is rotated, then again you close your eyes, then your friend will rotate by another 120 degree. That means 120 plus 120. When 240 degree angle was rotated, again the configuration of the triangle looks as if it was original. And therefore, you will be unable to distinguish the current configuration from the original configuration. And we say that 240 degree rotation is the second symmetry element in the system. And similarly, if you rotate once again by another 120 degree, that means 120 plus 120 plus 120, that gives you 360 degree rotation. You again see the original triangle, and therefore you will be once again unable to distinguish from the original configuration. We say that this is identically the same as the original, and therefore we give this particular name called identity. Because 360 degree is something special when compared to other values. 360 degree rotation will be generally the symmetry element for any object. Okay, you take an arbitrary shaped object that doesn't have equal values of the length of the sides of the triangle. Whatever triangle that you take arbitrary, make 360 degree rotation, you get the original. So 360 degree rotation is something what you can call the identity element. So now we are going to catch the technical words or the technical jargons. One is the symmetry element. So symmetry element is one of the technical words that you'll have to catch. The second thing is an identity element. So you understand what is an identity. Okay, that means 360 degree rotation, which is equivalent to 0 degree rotation, is what is referred to as the identity element, and this also happens to be symmetry element. So how many symmetry elements are there? You can easily see 3 of them are there. We can now give mathematical symbols for that. We can give R1, for example, R2, R3. R1, R2, R3 can be the symbols that you can give. And then mathematically, if you ask the question, what is the R1? Is it a number? Can you say 120 degree? So the answer is not. The 120 degree is not the number R1, but instead we say that it's a rotation matrix. Because every rotation can be represented by a matrix that you already know. Okay, whether it is 2-dimensional or 3-dimensional. If it is 2-dimensional, it is 2 by 2 matrix. If the rotation is 3-dimensional, you already know that it is a 3-dimensional matrix, which are in particular the Euler angles that were there. So in general, now this being the 2-dimensional situation, automatically the R1 will represent a rotation matrix corresponding to whatever angle. Similarly, if you have 240 degree, then you have corresponding another matrix. So R1 will represent a 2 by 2 matrix, R2 will represent another matrix, and R3 will represent a 0 degree rotation matrix. So what you understand is that these are the matrix elements. So each one of the matrix is the mathematical object that we are going to have. And then what is the mathematical operation that you have performed is a rotation operation. So this is another technical word that we have to capture. Rotation is a mathematical operator. Operator is a word that you'll have to capture now. It is not addition, it is not subtraction, because as I already told you that we are going to make a generalization to the kind of mathematics that you learned in your school or your undergraduate, which means that when you learn something like addition, subtraction, etc., multiplication, division, now we are now in a position to grasp that other than these things, you can always have a large number of mathematical operators available to you. Okay. Right now, immediately what is visible to you? Right now, what is visible to you is the rotation. So rotation is a mathematical operator. That is what is a point to be noted. It is not a addition, it is not a subtraction, etc. So we are going to give a terminology called mathematical operator. And then we are going to give the terminology called element. So these are the terminologies we will be using when you are moving from a particular mathematical scenario to a more general system. That means we are going to describe the properties of several of the mathematical objects together. Okay, that kind of discussion is what is the process of abstraction. So let us once again let me move on to the board and then write down what are the topics or what is the terminology going behind the scenes. Okay, let me go back and then show that. So here let me therefore write down what is discussed till now, that we are making to move from the particular situation to the general situation. So as an example, what we can consider is a particular situation can be something like myself. Okay, either you write my name or you can write on myself. That can be generalized to a man. Okay, certainly you can see that man will be a generalization of individual. Again, if you generalize, it will be a human being, and if you generalize that, that could be a living being. So the understanding is clear that we are moving from a particular situation to the general situation, and this is what is known as abstraction of a concept. So this is the concept, and which means that it is very clear that it is not a difficult thing. So abstraction of a concept doesn't mean, so that is what I would like to write down, that abstraction of a concept doesn't imply difficulty to grasp. Okay, because generally students have an opinion that abstracting means something that is difficult to understand. Okay, so therefore I am going to write down that it doesn't mean that it is difficult to grasp, but instead of difficulty you basically have clear understanding. So rather than that, so what is the meaning? Rather than that, I will say that abstraction is an ability to discuss many things. I will write that. So instead of that, rather I will say that abstraction is the ability to discuss a wide variety. It's an ability to discuss a wide variety of topics. We can say like that. Okay, is a wide variety of topics using a particular notation. So the word abstract is very important. Otherwise, when you deal with a book on abstract algebra and then something called group theory, etc., you generally have a feeling that it is something too difficult, or it's a topic that is very dry and boring. Okay, that is not the situation. That's what I am going to write down, that abstract notation is what is very important. Once you understand the notation and in what way you are going to generalize, things become quite simple and interesting. So therefore I am going to give examples clearly so that nothing is difficult here. So abstract algebra is not difficult. So to start with, what is a notation is, plus is already known to you. I will write down that it is addition operator. It is very familiar. So you know that plus means addition operator, and then you can always have a usual multiplication, etc. Now what is the generalization is star. That is what I am going to write down. Instead of saying plus, minus, etc., now you write down star. Star means general mathematical operator rather than saying addition, multiplication. Now there is a point to be noted that I would like to tell that the star is an abstract notation or an operator, and a plus means a particular operator. Now you see the generalization. Particular operator can be replaced by a generalized operator or abstract operator, star. But the star is something that you'll have to note down some point. I will write down here. When you are writing a programming, for example, in computer programming, star is used for a multiplication. So I want to now make it clear that star doesn't mean multiplication. This is a point to be noted. Okay, star does not represent multiplication, but rather I will say that star is generalization, or it's a notation by which you write down. So this is the first thing. So whatever I have explained, I would like to highlight. Then we will move on to the next one. So which is particular, which is general, etc. I am writing, but keep a note on the star. Star is not at all multiplication. So it means abstract. Okay, so once these things are clear, now we can now understand what do you mean by so you can now clearly understand what is the meaning of abstract algebra. I will now write down. It is a generalization of the simple school algebra. Okay, so I'm not going to write down the definition that appears in the book, etc. So my purpose is to explain to you in simple language. So I will simply say that abstract algebra is the generalization of the simple school algebra. In what way you are generalizing is to include a variety of mathematical objects. In which way you are generalizing, that should be explained, right? So we are going to generalize in such a way as to include a variety of mathematical objects. Not only that, with a variety of mathematical operators. That's the point. So therefore, now it is a time to explain what do you mean by mathematical object, because we are going to use technical term. One is the mathematical object. So remember that's called element. And then another thing is operator. I'm come to that later. So what do you mean by a mathematical object? So to start with, as usual, we start with your elementary school. The day you join the school, they will always teach you the numbers, right? 1, 2, 3. So therefore, the first mathematical object that you learn is numbers. So there are different types of numbers that we will see later. So first thing is numbers. The second thing is polynomials. Okay, the moment you learn little higher algebra, then polynomials, then you learn matrices. And as you come to the higher secondary, you also learn some vectors, and then you also generalize the vectors to tensors, for example, and so on. Okay, so let me therefore write down additional tensors could be mathematical object. These are not the only mathematical object. These are examples. Okay, starting with this, these are the example. You can now include whatever mathematical object comes into picture. Now coming to the operator side, you can you as usual start with addition and whatever you know. Okay, the standard mathematical operators that you already known to you, plus any other thing that you are going to add. Okay, so these are the usual and well-known mathematical operators to you. So all these things you can do, and in addition you can add the new things such as the tensor products, and just now you learned the rotation. You can include rotation as a mathematical operator, which means that you are performing some operation, right? Then only the triangle will rotate. That's why it is called operator. You can also use some reflection, dilation. Okay, this collectively it is known as transformation. So transformation means rotation, reflection, dilation. Everything is coming under the head of transformation. So as these dots that I have written is an indication that this is not the only list. It's a variety. Okay, so it is not an exact number of 5 and 6. Okay, this is an example or a sample for mathematical objects and operators. So like this, you can keep on adding number of mathematical objects and number of operators. So we would like to describe the algebra for all of them. Okay, that is what I would like to say, and we will see in particular in examples of the different numbers. Okay, so this particular terminology is important. That's why I would like to introduce the concept of different numbers. This is quite familiar to you, but at the same time, for the terminology, we will be repeatedly using the particular symbols. Therefore, I would like to write here so that you also refresh your memory and use those symbols. So we start with the simple set of numbers like 1, 2, 3, etc. Because this is how you learn, and we are going to call this set by natural number. Remember that the symbol that we are going to use is n, like this, with a double line for n, and it's called natural numbers. So what is important here in this particular discussion, so what is important is this one. So give the importance to the symbol that we are going to use for this kind of n. So n means natural number where the natural number doesn't include 0. Okay, so this is very easy to remember because this is how you learn from the school. From the day one you join, you learn only 1, 2, 3. 0 will not be added. Okay, 0 will enter into picture when you move on to the higher classes, and therefore let us add 0 to this. So this is the same order in which we will be writing. and give importance to the symbol that we are going to give, because the symbols are going to be frequently used in abstract algebra, and therefore by looking at the symbol you should be able to, if you look at the symbol, you should remember that this is the set of numbers. So that kind of recognition is what is required. Okay, so let us now write down by including 0. So I am going to add 0 to the set of natural numbers. So 0 comma all n you write down there. So that kind of a set is known as the whole number. So let me put a capital W with a double line there. Okay, that is how you write. And we will call this as the set of all whole numbers. And then what else is missing is that negative numbers are not there in the list. As you can see, only positive numbers are there. So let us add negative numbers. So I will now put negative of all the natural numbers minus n. Then you put a 0. Then you put all the positive of the natural numbers. So that collection, the entire collection, is what is called the integers and then represented by capital Z. So Z is something that may be confusing to you because it looks like complex number, but it is not so. So it is a double-lined Z. Okay, that is a standard notation for the set of all integers, including negative values and 0. So the capital Z, remember, it is not complex number, but it is set of all integers. Okay, so all these things are integers only, but what about the fractional or decimal values? So that question naturally comes. So let us therefore include or how to represent the fractional and the decimal numbers. Because the fractional numbers are known as the quotients, we can also call it quotient. So where something by something, it is a standard notation to write P by Q, some number divided by some number, which cannot be simplified any further. If you are able to write like that, and where P and Q belong to the set of all integers, okay, where you can't cancel further. And Q not equal to 0 I am writing because infinity will enter into picture. So that's all about it. We will be representing by the symbol capital Q. Okay, so the point to be noted here is that the capital Q is the symbol that I would like to emphasize with a double line there. Okay, so everywhere you see that the double line will be there. For Z double line, W also double line, N also double line. So the points here that are written is that this is the belonging. Okay, P and Q will belong to the Z, means you already know what is Z. So they have to be one of the numbers belonging to the Z, excepting 0, because if 0 comes in the denominator here, infinity will enter into picture. So infinity is not a number. Okay, so it is a very large number, that's all. So it doesn't represent a particular number, therefore that should not be entering into picture. So to be careful on this kind of technicalities, we write down all these points. Otherwise, it is just enough if you write only P by Q. Okay. So this particular set of all numbers written in the form P by Q is known as rational numbers, and Q is used because it is also known as quotient. Okay, something with a division. So we will write down that this is the rational numbers. But then there are some other number, something like pi. Pi cannot be written down as a fraction of two numbers. Then what will you do? So let us therefore represent that. So let me write down then what happens to the numbers that cannot be written down as Q. So I will write it down as Q bar. Q bar means what? Q bar means all numbers that cannot be written down as Q. So I will explicitly write down that they are the set of all numbers that cannot be written down as P divided by Q. So any number that you can't write down as P divided by Q, we will call it by the symbol Q bar, and the name for that is known as the irrational numbers. So the previous one is rational, so this one is irrational. So example, what are the numbers that comes under this category? Something like pi. These are well known to you. Pi cannot be written down as a fraction. Similarly, square root of 2 cannot be written down. There are many numbers are there. Logarithm, the natural logarithm base, E, that also cannot be written. But this is not the only list. There are so many numbers are there which you cannot write down as a fraction. So the set of all numbers are known as Q bar. Remember, bar is there. Okay, Q bar is the set. So once these things are clear, then we will ask the question, what about, is there any other number, or that's all exhausted? So that is what we are now writing. Then we have still more numbers are left out. So let me write down therefore, if you combine all Q and Q bar, what will happen? Okay, set of all Q together with, that together with is what I am going to write down as a union. Union means together with. Set of all q together with q bar, we are going to give the name R, capital R, known as the set of all real numbers. So once again, remember, the capital R has a double line. So that is the standard way to write down. And the capital R is very important. Frequently we will use. Capital R is the set of all real numbers. And finally, once everything is over, only one thing is missing, namely complex number is missing. So let me write down that. Set of all numbers that can be written down of the form x plus iy, where I is equal to square root of -1, which doesn't belong to any of the previous list. Okay, that is what is denoted by the capital C. You see that C will be there, but once again double line is there. So that C will be the set of all numbers. These are known as the complex numbers. So once you have this, almost you have written down everything. That remember what I am trying to explain. X is belonging to the real number, Y is belonging to the real number. Both of them are real. Only x plus iy is complex number. Okay, x is real, y is real. So let us separate one with the another. So let us go up. So you can see the distinction, which is q bar, etc. And with that, we have the set of all numbers available to you, and very important is the notation. Okay, capital N, capital W, capital Z, capital Q bar, and then finally we have a capital R and then capital C. So the symbols are very important. I am emphasizing once again. So let us now represent which is a bigger set and which is a smaller set, because this will give you a good idea. So let me therefore write down, because so many things are there. I would let us see which set of number is a larger set and which set of number is a smaller set. It's quite simple and very easy. Let us spend only 1 minute. It may not take 1 or 2 minutes. That's all. Let us see which is a smaller and a larger set with a schematic diagram. So let us draw with a schematic diagram, then it will be easier. Schematic means something with a circle. Okay, we can simply represent how big or how small. So the smallest one is the set of natural numbers. That is the smallest number, because 0 is not there, right? Only 1, 2, 3. Now add 0, then it becomes a slightly bigger set. That's what I am trying to say. So what you understand is W is larger set than capital N. If then capital Z, what will happen? Capital Z will include a negative number, positive number, 0. So that is a much larger one, right? So that visibility is there in this diagram. That's what I am trying to say. By drawing this, we will be able to see much better visibility. And what do you mean by Q? Q is the ratio of all numbers, plus value, negative value. It's a ratio of all of them. So it is supposed to be much larger than Z. Then you have something called Q bar. Q bar is the set of number that cannot be written down as Q. So it has to be away from that. Q bar cannot stay inside that bigger white color circle. So therefore I am separately drawing, and now we are going to combine everything. Combining is what is known as a union. So I will say that Q and Q bar is union. There is a Q and there is a Q bar. I am just joining everything together, and you know what is the name for that. Q together with Q bar is capital R, known as the set of all real numbers. And if you take two real numbers and then add, you get a complex number. That's what I'm writing C there. For complex number, how many numbers you need? I need two real numbers. That's all. X plus iy, right? So x is one real number, y is another real number. So two real numbers are there, right? Therefore, it is a bigger set. Therefore, the C will be much more bigger set. So that's all about it. The very important point that you will have to remember is that the C and the capital R, they are the bigger sets, which we are going to use frequently. So this is the point to be noted. We will be using frequently capital R and capital C, most frequently, and the next frequent thing will be capital Z. So therefore symbols are important. Which is bigger is also important, because you can perform a large number of operations whenever you have bigger set. If you have small set, you can't perform many operations. Okay, so that's all. Whatever I explained, I have written down there. Give the importance to the symbols. And once you have finished, now the question is that what to do with these numbers. Okay, you have a lot of numbers, right? What to do with these numbers? The answer is quite clear. We can perform some mathematical operation. Let me write down that. So what we can do with numbers means we can perform some mathematical operations. Then the question comes, if you want to perform mathematical operation, are you going to perform operation with how many numbers at a time? If I give you 20 numbers with you to you, can you perform mathematical operation with all 20? The answer is no. That is what I am writing. You can perform mathematical operation only 2 at a time. Even though you give me 20 numbers, only 2 can be done. And therefore, we give the name binary operation or binary operators. So the terminology, how it is coming, therefore you don't have to worry. Whenever you see the terminology binary, you don't have to worry. This is very important. This concept is very important because this is appearing to be very simple, but this is quite important. If I give you 3 numbers, okay, I will give you 3 numbers to you, 10 plus, 20 plus, 30, add. Then how will you add is what you have to think. Can you add all 3 together or only 2 at a time? You can only take 2 at a time and then add. Then you add it to the 3rd number, and whatever result comes, then you add it to the 4th number. This is what you do. Okay, so therefore the fundamental point which goes very important here is that we can perform mathematical operation with 2 objects with you. The object is a number. Whether it is a number or it's a matrix, whatever be the case, you can only take 2 of them. If I give 3 of them, you will not do. You will store the 3 numbers with you, but you will perform the operation 2 at a time. This is very important. This concept is going to be there everywhere, and therefore, because only 2 numbers or 2 elements we are going to take, the operator is known as binary operator. So in the abstract algebra, this particular word will keep on coming, and therefore there is nothing to worry about. You understand clearly that whether it is addition, subtraction, rotation, whatever you are going to do, we are going to perform with only 2 mathematical objects. Okay, a number is a mathematical object. A polynomial is a mathematical object. So you will be doing a calculation only with 2 of them at a time. That's all about it. So the terminology is clear. Therefore, I will write down therefore what is the symbol for the binary operator. So what is the generic symbol? So let me therefore write down that. Generic symbol can be a small circle. So remember, it's a small circle, or it can be a star. So in the books, usually star will be printed, but sometimes drawing the star may be sometimes difficult. So you can use a small circle. That is a generic symbol. Okay. Particular symbol you already know, plus, minus, etc. So generic symbol is what we have to be careful, and therefore once you have this, we will ask the question, what are the properties of different operators? You can't have same properties, right? Different operators will have different properties. That is why the trouble comes. So let us see an example, which is quite familiar to you. Nothing is new here. Everything is familiar to you, but we will have to grasp the things together. If you are going to consider scalar numbers, simple numbers like a and b, then ab equal to ba. But what will happen if they are matrices? They are not equal. AB is not equal to BA for matrices. So therefore, when you are talking about the product, okay, you cannot always say that AB and B are equal. So this kind of situation demands that we have to study, or we have to classify the objects based on these properties. So I will write down that some kind of classification. This classification is also another known as grouping. Okay, whether it is grouping or classification. So what are you going to group is the mathematical objects we are going to group. Therefore, group the objects based on the properties. So what is clear from here is that the operators have the properties, and this kind of grouping job, we are going to perform some grouping job or grouping study, is what we call the group theory. Okay, either you can say that group theory, or better word is abstract algebra. So abstract algebra is a generalization, the most general one. Group theory is again a particular situation. So therefore you understand from where the group theory is coming, and what do you mean by an abstract algebra. It's all based on the properties of a binary operator. You always have a binary operator with you, and the properties is not the same, and therefore we will give the technical term for properties is axioms. Properties is fine, okay, but mathematicians have discovered a technical jargon known as axioms. Finally, it's the same whether you call properties or it's axiom. Ultimately, the meaning is same, but better to know the technical terms. They are known as the axioms means properties. Fine. So let me highlight what are the terminology which are important here. So what is important is scalar values and the matrix. There is a difference. Because of the scalars and because of the matrices, these kind of different things have come, and therefore there is a name for that. That name, let me write down. These are known as mathematical elements. So I am talking about the terminology, element, or it could be a mathematical object. So you should know what do you mean by element. You should know what is meant by a mathematical object. Scalar is an element. Matrix is an element. That is the distinction I am trying to say. Polynomial is an element. Each one is an element. That is known as an element. So now you are able to clearly distinguish which is an element and which is an operator. Okay, so once this is clear, let us move to another place in the board. Okay, now let us consider our triangle example, because we started with the triangle example. So once you are going to consider the triangle example, what could be the set? How do you write the set? Let us see that. You know what is a natural number, you know what is a whole number. Like that, can you write the set? The answer is quite simple. I already gave the answer in the beginning. It is the set of all rotations which give you the original triangle. That means 120-degree rotation, 240-degree rotation, and finally 360-degree rotation. Only these three things give you the symmetry elements. Okay, other angles, they don't give the symmetry elements, therefore we don't write. So there are only three. Let us give some mathematical symbols for that. R1. We can give anything you like. Let us give an R1, R2, R3 because it represents rotation. So therefore, whenever you are going to deal with a particular situation like this is how you are going to write down in a mathematical way. Okay, now you understand what is meant by abstraction. Abstraction means you give the notation for whatever it is and then consider that as a set. And once you have the set, you also tell what is the operator, rotation operator. You are going to tell that. So what is clear here is that each one of the element is a matrix. Because R1, R2, R3, each one is going to be a matrix. And once matrix is clear, elements are clear, then what about the operator? So idea is clear, right? You should have an element, you should have an operator. Only then you can have an abstract algebra. So the next question is, what is the operator? So let me clearly write down what operator you can talk. Can we say addition? Oh, why don't you talk about addition, subtraction? Is it possible? That is what I mean. Meaningful means if I say addition is operator, is it meaningful? So let us understand what it is. So can we do, or let us see what is addition is. We can perform the addition, but it doesn't give any meaning. Okay, come to the multiplication. We have two matrices, R1, R2, R3. You understand, right? Whether it is addition or multiplication, matrices. Matrix also we can multiply. But is it meaningful? The answer is yes. That is what I am going to write. There is a meaning. What do you mean by what kind of meaning is coming is that one rotation followed by another rotation. So if you are going to perform two rotations, one rotation followed by another rotation is the meaning given by the product of the two matrices. That is the meaning. In the case of the addition, you don't have such a meaning. Therefore, it is a meaningless operator. We don't want to perform that. So the answer is very clear that the matrix multiplication is a meaningful operator. That is what I am going to write down. R2 circle R1. Okay, the small circle is the binary operator. Okay, even though I am writing, let me write down clearly, it's binary operator. Because two elements are there, R2 and R1. Okay, and in some textbooks, the small circle is also known as composition operator. So there is nothing to worry about the terminology. Either you say it's a simply binary operator, and then sometimes this is also known as composition operator, because you are going to compose it. Compose means you are going to generate a new configuration. Composing means generating something new. Configuration means the way in which the object is lying. In our case, it is triangle. So whenever you take a particular subject or a particular situation, you have to discover the element. You have to discover the operator. And once you have these two things, the question is properties. You need to study the properties. I have an operator, I have an element. Then what to do? So therefore, now let us see what are the properties. Therefore, there is one important property of the binary operator. So that is very important to be noted. So I will write down that. This property goes without saying. That means whether you tell or not, binary operator means it has a property. What is that property? Let me write down that. The property is this. How will you perform a binary operation? I will write down that. You can perform the binary operation just like 1 plus 2 equal to 3. I take one mathematical object, then I perform an operator with another mathematical object. Small circle is operator. Okay. One mathematical object operated on, that is an operator. Okay. Mathematical binary operator operated on another mathematical object that will give me yet another mathematical object. Mathematical object is known as element. One element with an operator with another element will give me a third element. That's all about it. It's that simple. So now the question is, what is the point to be noted here is that the mathematical objects, whatever that you are going to have, that means 3 of them are there, they belong to which set? So you have to see that how many of them? 3 of them are there. How many mathematical objects are there? That should be clear. Then only you can understand. So there is the first one, then second one, and the third one. So 3 mathematical objects are there, or elements are there. So we have 3 elements. Where is the first one? Yeah, that is the first mathematical object. Second element, third element. Element means object, both are same. So if you want, I will write down that. So there are 3 mathematical objects or 3 elements. So I will write down that element and mathematical object are basically the same thing. So we have 3 elements, and now the condition comes. This is important. And if condition is important, if all these elements belong to the same set, all these elements belong to the same set. The word same is important. Same set. Okay, if that condition is satisfied, then we say that the binary operator is having the closure property. So it's very simple thing. Therefore, there is nothing to worry here. Everything belongs to the same set. That's all. You should not go outside the set. That's the meaning. So conceptually, it is very simple. There is a if condition there, and then same condition should be coming, and the binary operator is going to have the closure property. Closure is nothing. Okay, let me therefore explain in one word in a very simple language, so that closure means nothing difficult. See, if you take 2 tomatoes and 3 tomatoes and add 2 plus 3. Okay, so 2 plus 3, if you add, 5 is coming. That is okay. Number wise 5. This side is 2 tomato, right side is 3 tomato, and when you are adding, 5 is okay. But the question that we are asking is it the tomato or will it become brinjal after adding? So that is called set. Set means number wise it's fine, but whether the mathematical element is behaving the same way or it goes to another set. Okay, one set is it is like one basket full of tomato. That is one set. Another set is you have another basket full of brinjal. This is another set. When you are adding 2 two numbers of the tomatoes, tomato will not become brinjal, right? If that is the situation, that is very clear to you. If that is the situation, we say that the addition is closure property. Closure property means it belongs to the same set. It doesn't go to another set. If this is true, okay, for a simple addition, it is quite trivial and therefore you don't give any importance or you don't feel excited about that. Okay. But what happens is in the general mathematical objects, this is not true. When you add or when you subtract or whatever it is, when you perform some kind of a mathematical operation, what is very important is that there are chances that it will go to another set. This is where the problem comes. Therefore, we need a definition. Now, that definition is called the closed property. What is closed means the set is closed and you should not go outside that set. In case if it so happens that you have to go outside the set, then we say that the closure property is failed. Okay, the closure property is failed means we say that the binary operator is not at all an operator. We don't call that as a binary operator if that situation happens. So what is very important? So that is very important. Binary, the word binary operator has an implied meaning. Okay, what is meant by an implied meaning is that it has a closure property. So these two things has to go together. If the closure property is not there, there is no binary operator at all. Once there is no binary operator, there is no question of group theory. That's all. There is no group, nothing. There is no group, there is no field, no vector space, nothing is there. So this is very fundamental and therefore binary operator is something that has to exist. If the operator itself is not existing, there is no question of grouping at all. So that is why this is, even though it is quite simple thing, this is also a topic that you have to be carefully understand, and there is nothing difficult here. Closure is very simple, right? It has to belong to the same set. So let us see with an example, then things will be clear. So whatever I explained, let me write down. If the closure property is not satisfied, then we will not call that operator binary. That's all. We will not call the operator binary. That is very important. Then what is that operator means? That operator we don't want. So it is not at all a topic of interest, and therefore we don't talk about that operator. That's the meaning of that. Okay. So therefore let me write down in a kind of a conclusion here. So that of course the things are quite simple, as you can see. At the same time, you should also give importance to the conclusion. The conclusion is that the implied property is closure. Implied means, what do you mean by implied is, the moment you say binary operator, closure is implied. You don't have to check. That's the meaning. In case if the closure is not satisfied, the word binary is not meaningful. So this is the point that is very important. Very important. Okay. So therefore, you have to be careful with the word binary and closure. Binary and closure will go together, hand to hand. So to give an example, quite simple example, let us come to an empty part of the board. Let us divide it, this portion of the board, and I would like to write down here a simple example. So consider a small set of numbers. Okay, something like 1, 2, 5, 10. Okay, that's enough, not many. So you have only 4 numbers. Okay, that's the kind of a set that you have. And now the set is very clear. 1, 2, 5, 10 is element. And let us define an operator known as addition. Let us consider addition as an operator, because this is the simplest situation you can consider, and now you will be able to grasp what is the point. Now let us now add 2 things. What will happen if 1 plus 2? 1 plus 2 is 3. But where is 3? 3 is not there. That is what I'm writing, that 3 doesn't belong to our original set. Yes. That's all. This is the point. We write like this: 3 does not belong to, that is a symbol, does not belong to the S. S means set. And because of that reason, we make a conclusion that, or we say that closure property is not satisfied. We say that the closure property is not satisfied. So is this point is clear? You have a set, you have an operator. You can quickly make a decision whether it is a closure property satisfied or not. If you perform mathematical operation, then the answer should be inside that set. The answer should be inside that set. Okay, that is what we mean to say. So in our situation, we don't have that, and therefore we can't have a binary addition operator for this set. Okay, for this set, let me write down that. Okay, so this is the conclusion. The conclusion is we cannot have a binary operator as addition for our problem. For our problem means for this particular set. If this is the set given to you, and if the addition is given as an operator, the question is, can you qualify this operator as a binary operator? Can you give that qualification to that? The answer is no. We cannot give the qualification to the addition operator as binary operator. We will disqualify. Why? The reason is, if you add two elements, one is an element in S. S means set. One is an element in the S. Two is also an element in the S. But if you perform the addition, because addition is the operator that you have, I am getting an answer 3, but 3 does not belong to the set. That means you have to go outside that set. And the moment you say that we have to go outside the set, we reject that particular operator does not qualify for being the binary operator. And once the operator itself is not binary, there is no question of group theory. That's all. Okay. So that's why it's so fundamental that the closure property has to be satisfied at the very basic level. Okay, otherwise the whole thing fails. So now you understand what is the importance of the closure property, and it is easy to understand also what it is. Fine. So let us go back to the what I have written. Now once this is clear, you can now easily understand what is written there. Now you can read and understand what is there. Okay, if all the elements belong to the same set is very important. Only then the binary operator is having the closure property. So that's clear. And then you also read how the 1 plus 2 equal to 3. That is what is this one. Okay, that is an example. Okay, the 1 plus 2 equal to 3, what I am trying to say is that is exactly the same as what is written this side, namely one mathematical object, then another mathematical object will give you yet another mathematical object. That is what is meaning. So that is an example. Now we'll come here. Let me explain here. What is there is multiplication. Let me write down that. You have a multiplication operator in the AB. Okay, even though you don't put a dot and a cross, that's the meaning. So we would like to express a terminology corresponding to this. So instead of saying simply AB, now let us introduce the star notation. So A star B equal to B star A. That is what is the meaning of AB equal to BA. Now we are explicitly writing the star. Okay, so star is a general or a generic operator. It can be anything. That is very important. It is not multiplication. So if this particular condition AB equal to BA satisfy, then we will give the technical name called commutative property. So just now you learned the so-called closure property. So in that particular style, the technical term for the equality between AB and BA is commutative. So this is important. Star means generic. Generic means any operator. It can be any operator. So that point should be clear, because our mind will always tell that star means multiplication. It is not so. Okay, then you take the case of matrices. It is very trivial for you that A plus B, B plus A are equal. If it is equal, then we say that it is additive. Addition is commutative. Or we say that the property is additive commutativity property. In the case of the multiplication, it doesn't happen. Therefore, we say that the multiplicative commutativity is absent, or it is failure. So it is very clear now how to understand the commutativity property. Commutativity is something that is common. You can apply it for addition, you can apply it for multiplication. So commutativity is the ability to stay with inequality. Okay, the ability to stay equality is what is important. So as you can easily see that there is an equality here. If the ability is there to stay equal, then we say that the commutativity property is successful. If the equality is a failure, then we say that the commutativity has failed. So that is how it is. So therefore, whether it is a simple addition or simple multiplication, whatever it is, in general we will represent it by a star notation. If the star notation is not there, sometimes you can also put a small circle notation. Okay, one of these two things are generally used. So therefore, rather than specifically talking with respect to the plus and the multiplication, we will talk in a general way like A star B. That is what we have written here. And then I put an if condition. If the condition satisfies, that means if the equality, if means equality. So if the equality condition is satisfied, okay, then the star operator has the commutative property. So this is always, it will always not satisfy. So this happens to be an important classification. We are going to talk about the commutative group and the non-commutative group. So therefore, the distinction comes from this particular simple concept, and therefore you have to give attention to this. In the case of the matrices itself, we can see that additive, it has possessing commutativity. You have yes here, you have no here, but the object is matrix alone. So even though the mathematical object is matrix, when the operator changes, commutativity fails. So these things are valid for matrices. So therefore I will write down for clarity that the discussion that we have made right now is valid for matrices. So in continuation, once you have the concept is clear for matrices, we can move to a next mathematical objects. Okay, something like vectors. We can consider the Euclidean vectors and then discuss about it. And probably let me write down the title. You can consider the Euclidean vectors and then discuss the similar scenario. So whatever I am writing should be quite simple, so that I have not explained. As you can see that when you take the two vectors, you can add them, equality will be there. Cross product, you already know that the negative will come here and therefore it is not equal. Scalar product is equal, and therefore what happens is the addition operator, you say yes. What do you mean by yes here? Commutative property is satisfied, yes. And for this particular situation, commutative property is not satisfied. That is what I mean to say, no. And similarly for the case of the dot product or the scalar product, again the commutative property is yes. So as you can see that when the mathematical objects are vector, now here you see mathematical object is a vector, and then you have different operators are there, and depending on that whether the commutativity is present or not, it changes. So our conclusion is very clear that depending on the mathematical object that you are going to take, and together with what kind of mathematical operator that you are going to consider, whether it is going to be commutative or not, we do not know. We have to perform and then verify. So in some cases it will be commutative, in some other cases it may not be. And therefore the grouping is also based on this important property, and whenever the answer comes yes, we say that it is commutative group, and whenever the situation happens to be no, we say non-commutative group. So this classification is going to be important. That is why I am giving these two examples. So the classification is based on only one property. So there is nothing to worry too much about the commutative group. Sometimes commutative group is also known as abelian group. That's all about it. But the checking that you have to do is only one check. That means for a given operator, for only one operator, which operator is given, only for that you have to check. Now in this particular case, we are considering different possibilities and writing the different situation. If you are going to consider a specific situation for a group checking, then only for that particular operator, whether it is this or that, whatever it is, only for a particular operator you have to check. And based on that, you can easily classify whether the group is commutative group or non-commutative group. So these are the, as you can see, that we have not written down any textbook definition, like you might have seen already the textbook definition, that immediately you write down some properties and say that if these properties are satisfied, then we call this as a group. So that is how it is written in the textbooks. But however, we are not going to write down like this and then asking you to memorize. So that is not the idea. The idea is that you can easily understand how things are evolving. Now you can see that starting from what is already known to you, starting from your school mathematics to the whatever mathematics that you already know, how you are proceeding further, or what is the methodology of moving to the generalize the situation corresponding to various mathematical operators and various mathematical objects. So that is the idea. And once you have this, you can easily define the concept of group. You can define the concept of a field. And once these things are clear, we are ready to define what is known as a vector space. So the definition of a vector space is based on the definition of a field and the definition of a group. So that is why I am taking considerable amount of time to introduce the terminology. So here the terminologies are clear. Till now we have seen the closure property as one important terminology. Binary operator is another terminology. The elements or mathematical objects, another terminology. And finally you have the commutative property as another terminology. So in addition to that, you need one more terminology is required. Once that is the terminology is also introduced to you, we are ready to define what is meant by vector space. Okay, so that part, okay, that there one more terminology and then the definition of the vector space we will discuss in the next class. Okay.